Imagine a place in the universe where the rules of reality break down, where gravity is so powerful that nothing, not even light, can escape. These are black holes, real, not science fiction. Born from the death of giant stars, black holes are the ultimate cosmic mystery. When a massive star runs out of fuel, it collapses under its own weight, squeezing all its matter into an infinitely small point. This creates a region of space-time with gravity so extreme, it tears a hole in the fabric of the universe. For years, black holes were only theoretical, places of absolute darkness and silence. As you approach one, time slows for you, while the universe races ahead outside. Cross the event horizon, the point of no return, and you're lost forever. Black holes challenge everything we know about physics. They are nature's most extreme creations, warping time and space beyond recognition. Their gravity is a bottomless well. Anything that falls in is lost, its information seemingly erased. Do black holes destroy information or store it in ways we don't yet understand? These mysteries draw us in, compelling us to study these dark objects drifting through the cosmos. Black holes are both the graveyards of stars and possibly the seeds of galaxies. Understanding them is one of science's greatest challenges. Our journey to uncover their secrets has taken us from theory to the very edge of reality. The story of black holes is a story of human curiosity and our relentless desire to know our place in the cosmos. Let's begin that journey. Our quest to understand black holes starts with Albert Einstein. In 1915, he introduced the general theory of relativity, revolutionizing our view of gravity. Einstein showed that space and time are woven together into a four-dimensional fabric, space-time. Gravity, he said, is the bending of this fabric by massive objects. Imagine space-time as a stretched rubber sheet. A heavy ball creates a dip, curving the sheet. Planets like Earth follow the curves in this fabric, not because they're pulled, but because they're moving along the straightest path in curved space-time. This idea explained planetary motion with stunning accuracy. Einstein's theory made bold predictions, like light bending around massive objects. In 1919, Arthur Eddington confirmed this during a solar eclipse, proving Einstein right. Suddenly, we had a new way to explore the universe's most extreme places. If enough mass is packed into a small space, could space-time curve so much it breaks, creating a hole nothing can escape? Einstein's equations hinted at something truly bizarre, a place where gravity becomes infinite. The mathematics pointed to an object stranger than anything seen before. The stage was set for the theoretical discovery of the black hole. What began as a beautiful idea would soon reveal the universe's darkest secrets. The journey into the unknown had begun. Einstein's equations predicted black holes, but he doubted they could exist. He saw singularities, points of infinite density, as flaws, not features, of his theory. Einstein believed nature would prevent such extremes, that some unknown process would stop a star from collapsing completely. In 1939, he published a paper arguing against the physical reality of black holes. He thought matter couldn't be compressed beyond a certain point, and the event horizon would never truly form. Even the greatest minds can have blind spots. Einstein's intuition failed him here. The universe, it turns out, is wilder than he imagined. While Einstein remained skeptical, other physicists pressed on, exploring the strange predictions of his theory. The idea of black holes refused to disappear. It lingered in the mathematics, waiting for someone to take it seriously. The next breakthrough would come from the chaos of war. Amidst World War I, German physicist Karl Schwarzschild solved Einstein's equations for a single spherical mass. His solution described how spacetime curves around a star or planet, a mathematical masterpiece. But hidden in his work was something strange, a critical radius, now called the Schwarzschild radius. Squeeze enough mass inside this radius, and spacetime breaks, a point of no return, the event horizon. Inside, all paths lead inward, escape is impossible. Schwarzschild had unknowingly provided the first mathematical framework for a black hole. Tragically, he died soon after, but his legacy endures. His solution gave science its first glimpse into the bizarre reality of black holes. The Schwarzschild radius remains fundamental to our understanding of these cosmic monsters. From the trenches of war, a new kind of object was born. For decades, black holes remained mathematical ghosts. Most physicists dismissed them as oddities, too extreme for nature. In the late 1930s, Oppenheimer and Snyder showed that a massive star could collapse past its Schwarzschild radius, forming a frozen star. Still, there was no evidence, just theory. The term black hole wasn't coined until 1967 by John Wheeler, who brought the idea into the mainstream. The name captured imaginations and sparked new interest. But how do you find something that emits no light? Astronomers realized they could look for the effects of black holes on nearby stars and matter. The hunt for real black holes was about to begin. The 1960s and 70s brought a revolution in X-ray astronomy. In 1964, a rocket detected a powerful X-ray source in Cygnus X1. It was a mystery, a bright X-ray beacon from an empty patch of sky. Astronomers found the X-rays came from the same spot as a blue supergiant star. But the star alone couldn't explain the intense X-rays. The star was wobbling, as if orbiting an invisible companion. By measuring this wobble, astronomers calculated the mass of the unseen object, about 15 times that of our sun. Too massive to be a neutron star, it could only be a black hole. The X-rays were matter being torn from the star, heated as it spiraled into the black hole. The discovery of Cygnus X1 was the first strong evidence that black holes were real. The debate was so fierce that Stephen Hawking and Kip Thorne made a famous bet about its nature. As evidence mounted, Hawking conceded, Cygnus X1 was a black hole. The ghost had become reality. We had found our first black hole. Black holes were no longer just theory. They were out there, lurking in our galaxy. The search for even bigger monsters was next. The stage was set for the hunt at the heart of our galaxy. Cygnus X1 proved stellar mass black holes exist, but theory predicted even larger ones, supermassive black holes. These giants, millions of times the sun's mass, were thought to lurk at galaxy centers, including our own. The center of the Milky Way is hidden by dust, so astronomers used radio and infrared telescopes. In the 1970s, they found a bright, compact radio source, Sagittarius A. Its true nature was a mystery. Was it a dense star cluster or a supermassive black hole? Two teams, led by Reinhard Genzel and André Ghez, tracked stars orbiting close to Sagittarius A for decades. The stars whipped around an invisible point at incredible speeds. Calculations showed this object had a mass of 4 million suns, packed into a tiny region. Nothing but a supermassive black hole could explain it. We had found the monster at the heart of our galaxy. For all the evidence, no one had ever seen a black hole until recently. The answer wasn't to photograph the black hole itself, but its shadow. Einstein's theory predicted a bright ring of light around a dark shadow, cast by the black hole's gravity. The challenge: even the largest black holes appear tiny in the sky. The solution: the Event Horizon Telescope, a global network of radio telescopes acting as one Earth-sized eye. In 2017, the EHT targeted two supermassive black holes, Sagittarius AI and one in Galaxy M87. After years of work, in April 2019, the world saw the first direct image of a black hole. The image showed a fiery ring around a perfect circle of darkness, the black hole's shadow. It was fuzzy, but it was real. For the first time, we weren't just inferring black holes, we were seeing one. Humanity had glimpsed the unseeable. Einstein's theory was proven right in the most spectacular way. The age of black hole imaging had begun. Black holes have gone from mathematical curiosities to central players in our understanding of the cosmos. Supermassive black holes shape galaxies, anchoring them and regulating star formation. They're not just destroyers, they're cosmic architects. Black holes have also given us a new way to listen to the universe. In 2015, LIGO detected gravitational waves, ripples in space-time, from colliding black holes. We can now hear the universe's most dramatic events, confirming Einstein's predictions. Black holes force us to confront the nature of time itself. Near a black hole, time slows dramatically, a fundamental feature of our universe. They are natural laboratories for studying gravity, space, and time. Our quest to understand black holes is just beginning. What lies beyond the event horizon remains a mystery. Black holes point the way to new physics, uniting relativity and quantum theory. They are the ultimate